Hello, Royals. For lesson 2.4, let's just do a quick review of our four parent functions, focusing on our two new parent functions. And then I want to show you what you should do when you encounter a different parent that doesn't look like a transformation of these. In our lesson, we started with tables of values for these curves, but you really want to get to the stage where you recognize them without having to do a table of values. Okay. I've changed the letters just so that you don't get used to the exact same letters. This is a line with a slope of 1 and a y-intercept of 0. X is equal to y, or your output is the same as your input. You should be very familiar with your parent quadratic. We now know that I would like you to focus on the behavior between 0 and 1 a little bit more, though. Your function is temporarily horizontal at the origin. Okay, so here's the line y equals x right there. The square of 1/2 is smaller than 1/2. Squaring doesn't make everything bigger. That's very important for the radical function. The nice thing is that you can see a table of values in your head here. I sometimes see students say, I can't remember which one is which, and that's a nonsense argument because you shouldn't have to remember. No one's asked you to remember. But I mean, let's talk about the fact that you are allowed to take the square root of 0, and the square root of 0 is 0, and the square root of 1 is 1, and the square root of 4 is 2. So there's not like, oh, I couldn't remember if it's this one or that one kind of thing. Just like how the parent quadratic is horizontal at the origin, the parent radical is vertical at the origin. The square root of 1/2, the square root of 1/4 is 1/2. Square rooting does not always make your outputs smaller. That's not true between 0 and 1. So get this curve. I even want you to stress it. It is vertical originally, just temporarily. Okay. And then m of x, your rectangular hyperbola or your parent reciprocal, the reciprocal of the line, will treat as a type of alteration of your parent line. Is this curve with two perpendicular asymptotes, a horizontal asymptote of y equals 0, a vertical asymptote of x equals 0. The reciprocal of 1 is 1, reciprocal of 4 is 1/4, reciprocal of 1/4 is 4. Yeah. Okay. And again, you shouldn't have to rely on creating tables of values for these. You want to be comfortable with their rough sketches. But when you encounter a function, and a new function, and this should happen in the homework, you might want to resort to a table of values. So let's just look at three functions that we're not really going to transform in this course. We're going to see one of them a little bit later in the course, but you'll see these in advanced functions. We still should be able to investigate them and talk about things like their domain and range. Let's talk about f of x equals x cubed. Without actually constructing a table of values, let's just do one quickly in our head. I'm allowed to cube any number, right? So I'm going to predict my domain is unrestricted. The cube of 0 is 0. The cube of 1 is 1. The cube of -1 is -1. So it kind of is more similar to y equals x with an odd exponent than it is to y equals x squared with an even exponent. Negative inputs yield negative outputs. Positive inputs yield positive outputs. It's going to be steeper than y equals x squared eventually because the square of 2 is 4, the cube of 2 is already 8, and the cube of 3 is 27. But be careful about just making it steeper. It's actually shallower between 0 and 1 as well. The cube of 1/2 is 1/8, and the cube of 1/4 is 1/64. The cube of -1/4 is -1/64. The cube of -1/2 is -1/8. Curve, and you might want to plot it in Desmos to get an accurate sketch of it, because I'm going to be exaggerating the horizontal nature. Really want to stress that horizontal nature. I want to stress that the curve is above y equals x to the left here. It's below y equals x to the right there. It's temporarily horizontal right there. So I notice that unlike the quadratic, more like the line, its range is also unrestricted. Okay, you'll be working with transformations of cubics in advanced functions. How about, yeah, you know what, I'm going to skip that one. Let's just do G, I'm running out of letters, n of x equals the reciprocal of the square of x. So I'm wondering if it has features kind of like this curve because it's a reciprocal curve, and I'm wondering if it has features like this curve because it's a quadratic curve. Let's think about our domain and range here. Domain, I'm allowed to square any number, so there's no restrictions there. Am I allowed to divide by any number? No, I'm not allowed to divide by 0, and that means that an input of 0 would give me a division by 0, so x can't equal 0. Let's think about our outputs. Just like here, when I square outputs, if I square any number, I get a non-negative output, neutral or positive. Here, though, the input that would give me a neutral square of 0 is no longer acceptable. So I'm pretty confident saying that my outputs here need to all be positive. And because of that, I'm going to sort of change the focus of my, or the center of my sketch, like I did with H over here. I didn't bother putting the origin in the middle of my sketch. That would waste half of my space. All right, let's start substituting in some numbers. N of 1. Well, let's start by squaring and then reciprocating. The square of 1 is 1. The reciprocal of 1 is 1. So I'm going through 1, 1, just like every single one of these curves. This curve doesn't go through 0, 0. That curve doesn't. This one does, that one does, that one does, that one does. 2. N of 2. The square of 2 is 4. The reciprocal of 4 is 1/4. Here, an input of 2 gave me an output of 1/2. This is lower than that, closer to 0. Put in, I don't know, 4. N of 4. The square of 4 is 16. The reciprocal of 16 is 1/16. Substitute in 100. The square of 100 is 10,000. The reciprocal of 10,000 is 1/10,000th. So that sounds asymptotic. Let's substitute in some numbers between 1 and 0, just like we found was useful for our quadratic and our radical and our reciprocal and our cubic. N of 1/2. The square of 1/2 is 1/4. The reciprocal of 1/4 is 4. This curve is going through 1/2 comma, or sorry, 1/2 comma 2. This curve is going through 1/2 comma 4. N of 1/4. The square of 1/4 is 1/16th. The reciprocal of 1/16th is 16. Do you see how reading these fractions like 1/16th and 1/4 is probably better than saying 1/4 or 1 divided by 4, and definitely easier than doing things in decimals. What's 1/4? Well, 1/4 as a decimal is 0.25. What's 0.25 squared? I don't know. What's the reciprocal of 0.25 squared? I mean, my calculator is a hand reach away, but I don't need it if I work with fractions. Notice because of the even exponent, this function will have a type of symmetry here. What's the square of -1? That's 1. What's the reciprocal of 1? 1. What's the square of -2? That's positive 4. What's the reciprocal of 4? 1/4. What else did I put in here? 4. -4 squared is 16. The reciprocal of 16 is 1/16th. So it's symmetric. It has an axis of symmetry, just like y equals x squared does. 1/2, -1/2 squared is 1/4. The reciprocal of 1/4 is 4. I end up with a curve that has some features similar to my parent reciprocal. It has asymptotes at x equals 0 and y equals 0. It changes shape relatively quickly. It has some features related to h as well. Again, we're not going to be doing transformations of these two. We're not going to consider them parent functions in our course. But when you hit a new function, you can resort back to a table of values. Just don't be using a table of values for transformations, or you shouldn't have to write out your values here. If you're doing a table of values, it should be done in your head and relatively quickly. Okay. Check out Desmos to see more accurate versions of those curves.